Hello everybody. In today's video, we are going to solve another problem live on LeetCode from the top interview 150 problem list. So far, we have solved all the problems up to insert, delete, get random O of 1. If you haven't checked out my videos on those problems, please go to my channel and check them out. The next one is product of array except self. So let's read the problem. Given an integer array nums, return an array answer such that answer of I is equal to the product of all the elements of nums except nums of I. Okay, I see. The product of any prefix or suffix of nums is guaranteed to fit in a 32-bit integer. Yeah, basically, if we are given an array like this, basically any product of any subset of these elements is going to fit in a 32-bit integer. You must write an algorithm that runs in O of n time and without using the division operation. Oh gosh, okay. So as soon as I read this, I'm like, okay, an easy approach is to go through the array once, calculate product of all the elements, and then go through the array again and divide the value of that element from the total product to get the answer for that index, right? Looks like it is not that easy. They have prohibited us from using the division operation. Okay, well, we'll see. We'll see what to do. Let's look at the examples 1, 2, 3, 4. So, like the problem said, for the first location, we are supposed to multiply all the other elements 2, 3, and 4. So that's 24. For the second location, we are going to multiply everything except 2. So 1 times 3 times 4, that's 12. For the third location, it's 1 times 2 times 4, 8. And for the last location, 1 times 2 times 3, that is 6. Okay, the second example is -1, 10, minus. Okay, so this is interesting because it has a 0 in it, which zeros out everything else except itself. And itself is just basically a product of everything, which is 9. In fact, if there are two zeros, it zeros out everything, right? Yeah, actually it does. So if there is actually more than one zeros, then the answer will be all zeros because no matter what you pick, you have another zero which is going to zero everything out, right? Okay, so the constraints are that the length of the nums array is between 2 and 100,000 inclusive. Okay, wonder why 2? It's generally 1. Oh, that's actually because we are doing product of everything except self. So that's why they don't want us to bother about the special case of array of size 1. Then what do you count as a product except self? Well, I would consider it 1, but okay. We don't have to worry about it. And then the value of all the elements in the array is between negative and 30 inclusive. And yeah, that, I mean, negative, basically there are negative numbers, and that was clear from this example. Okay. The product of any prefix or suffix of nums is guaranteed to fit in a 32-bit integer. I wonder why they have given this. Even when I read it here, I was maybe that is somehow helps us with the answer when division is not allowed. But anyway, we'll see. And then the follow-up is, can you solve the problem in O of 1 extra space complexity? Okay. The output array does not count as extra space for space complexity analysis. Yeah, that is always true. We have to allocate an array to store the output, and that is not extra memory. Okay. How do we do this? So let's actually first, I mean, we should lay out the algorithm with division first. I mean, it's pretty obvious, but I wonder if that gives us any hints. So with division, right? So what we said is we basically say P equal to product of all elements. Now, again, zeros make this very interesting, but for a moment, just at least the simple case. And then for each element A in array A, the answer is P divided by A, right? Yeah, so that makes sense. Now the problem is 0. So in case there was a 0 in there, so 1, 0, 3, 4, for example. I mean, they have given an example with zeros, but I'll just modify this just to kind of see what happens. Yeah, I think in this case it won't work, right? Because P will be 0, but for most, so okay, so 0 divided by 1 works, so that becomes 0, but 0 divided by 0 is not defined, so we need to figure that out. and then 0 and 0, that works. So this algorithm still works except for the zeroth, the one that is 0. And so I think we also need to keep track of p dash product of all elements without except zeros, right? And that's because when there is a 0, then that will be the answer, right? But if there are more than one zeros, like I said earlier, then even that doesn't work. I think we just need to special case it. So I think our full algorithm is we don't need two products actually. We just need one product, which is p dash actually. So let's just call it p, and then we say p equal to, and then for each element a in a, we actually also say, one second, we also count zeros, okay? And then let's say zero count is equal to number of zeros, okay? So for each element a in a, if zero count is greater than 1, then the answer is 0, right? Otherwise, if zero count is greater than 0 or equal 1, I guess, then I think there are two cases. One case is that if it itself is 0, right? So 0, there is 1 0 basically. So if a equals 0, then answer is p, then answer is equal to p, else answer equal to 0, right? And then otherwise we just say answer equal to p divided by a, right? So I think this is the full algorithm, looks like. Okay. I don't know if it is worth implementing this. Like, you can pretty much translate what I wrote there into code, and that should work. Okay, now let's see how we can do this without division. Well, one thing I was thinking about, I'm not sure if it actually helps though, but let me share what I'm thinking, right? Like if we say, let's take 4 general numbers for now, just 4. Okay, and let's say we are trying to calculate a times b times c, right? And let's say we are able to go through the array once and make the, like, can we use subtraction? Basically, that's what I'm trying to think. Like, if we are not allowed division, can we somehow do subtraction? Because, you know, yeah, but the thing is, in this case, yeah, I don't think it works because we will actually have to subtract this, right? If there is d minus 1 times a times b times c, that's because this is d times a times b times c. So a times b times c is multiplied d times. If you consider this to be one number x, it is x times d is same as x plus d minus 1 x, right? So that's why this would be the case. But in this case, the problem is we recursively need the value of a times b times c. D minus 1 is not a problem. We can look up d minus 1 in O of 1. But the problem is it needs itself to calculate. Okay, so that doesn't work. I think let's go back to that why they were given prefix and suffix, right? So let's take this example and do like suffix and prefix multiplications, because they said, oh, they are supposed to fit in 30. I wonder why they said that. So let's say this is the prefix, this is the original array, this is the prefix products or prefix products, and this is the suffix products, right? So what are the prefix? Well, assume there is a 1 before and after actually, because when we do product, 1 is the default value, not 0. Okay, so before 1, what is the product of all the elements before 1? Well, 1, because I said we assume. What is the product of all the elements before 2? 2. What is the product of all the elements before 3? That is also, no wait, what is the product of all the elements before 2 is 1, before 3 is 2, and before 4 is 6, right? So yes, 3 times 2, okay. So that's that. Now let's come up with suffix products. So suffix products is, what is the product of all the elements after 1? 2 times 3 times 4, so 24. What is the product of all the elements after 2? That's 12. all the elements after 3 is 4, and all the elements after 4 is 1. Like I said, assume a 1 at the end as well. And yeah, so, oh, I see. So from this, the answer would be, you just multiply the prefix with the suffix, right? So 1 times 24 is 24, 1 times 12 is 12, 4 times 2 is 8, and 6 times 1 is 6. And the reason is because the 0th element here is the product of all the elements before 0th number, and the 0th element here is the product of all the elements after. So it's like saying, if you want a product without yourself, you multiply all the numbers before you, all the numbers after you, right? And we can do both of these in O of n time actually, right? In this case, we go from left to right and keep a running product. And in this case, we go from right to left, suffix ones, and we do. So we can create both the arrays in O of n time, and then we can construct this in O of n time as well. Okay, I think, and that's why, yeah, I think that's why they've given that constraint. Okay, so that gave us a good hint. So let's say, actually, yeah, we can just write it here. Actually, I don't know why I was creating a helper. Oh yeah, I think I know why. I mean, they've given a challenge, right? Like, can you do it without extra memory? So that's why I was thinking to do 2 versions, but we'll get there. Let's just write it here for now. So what we are doing is we are saying prefix prods equal to new int nums dot length, right? And actually, let's just first fill up prefix prod so we don't confuse ourselves. Int product equal to 1. This is what we'll use to do running products. And yeah, we just fill it up. So I is less than prefix prods dot length plus plus I. And then, yeah, so before we multiply ourselves to the product, we need to assign the product to the prefix prods at that location. So prefix prods of I equal to product, because it doesn't include ourselves, right? That is the definition of prefix product, which is product of all the numbers before us. Okay, and now we say product times equals nums of I. We multiply ourselves to the product because the numbers after us need us in the product. Okay, so that should do it. And similarly, we should be able to compute a suffix products. Suffix prods, well, product is already defined, and then we go from suffix prods dot length minus 1 and greater or equal to 0 and minus obviously minus I, right? And same thing, we first, oh wait, so this has to be suffix products. Suffix prods is I is equal to product. We first assign it and then we multiply ourselves to the product. Okay, so now it's easy, right? Now we just construct the answer products. Same thing, nums dot length, and we just I go to 0, I is less than products dot length plus plus I, and we just say products of I is equal to prefix, the product of all the prefixes of that number, right? So prefix prods of I times the product of all the suffix of that number. And note that here we don't have to handle zeros as special case at all because we are not doing division. That's at least one advantage of not doing division, I guess. So that's good. Okay, cool. That is let's just walk through this one more time. Like, I mean, this part is okay, but make sure that in that example we are doing exactly what we did here. So 1 1 2 6. Okay, are we doing that? So okay, so 1 2 3 4. So initially product is 1. We'll assign that to the 0th index. So yes, that's 1. But we also do product is 1 times 1. It still stays 1. We go to the next index. We assign that 1. And then we do 1 times 2. So that's 2. And the next index, yes, I think this should work. And then we do 2 times 3. Okay. So this is good. Let's run this. Okay, cool. I do want to add the test case with 2 zeros though. Let's add one here. I mean, it doesn't matter where we add based on how we have written the code, but okay, let's do this, and this should zero out everything. Okay, it did. Okay, cool. Let's try to submit this. Now they have given us a challenge of doing without extra memories. I'm pretty sure we are not going to beat many folks in memory. Okay, so we beat everybody in time, but in memory we only beat 19%. Okay, that's expected because probably a lot of people did that challenge. Okay, let's try to figure that out. Uh, oh, you know what? In fact, okay, I get it. So I was thinking about this for a second and then I didn't pay attention. So actually we can do all of this directly in the products array, the final products array. And okay, so here is what I'm thinking, right? And so let's just start doing it in the products array because we can just keep multiplying to that, right? Okay, so initially we are going to initialize the products array. So actually, let me first take the definition of that above. Okay, so here we directly say products of I, right? Equal to product. And here we basically, and here it was okay to directly assign it because, you know, we didn't, it was all zeros. So we should assign what is the prefix product there. But here we basically multiply to existing values, right? So products of I times equal to product. We don't want to erase what's there because it already contains the prefix product. So all we do is now also multiply into that the suffix product, right? Yeah, this should work. And we don't need this anymore. And that should work. Okay, let's see, let's see. Okay, compiler, that should, oh, of course. This is both products dot length. Yeah, I think. Okay, so that worked. Let's try to submit and see if we did better on memory and if we stayed the same on time. Okay, cool. So we did beat 100% on time and we beat about 70% on memory. Okay, that is cool actually. That makes sense. I think the main thing was the description. This gave a big hint. Not sure if I would have figured it out this way if they did not have this hint. Maybe eventually we would have, but that was a big hint. Like, why are they giving like prefix and suffix products? They all are guaranteed to fit in a 32-bit integer. This is why, right? Cool. Okay. Hopefully that was helpful to all of you. If you're liking what I'm doing on this channel, please consider subscribing to my channel and also hit that thumbs up button on the video if you can. Thank you. See you guys next.